Hello and welcome back. One of the key things about machine learning is that we learn from data. However, we need to understand what this actually means when we learn from data and what kind of pitfalls there are and what kind of things we need to think about when we learn from data. So the general machine learning approach is the following. We have data that can be, for example, structured data organized in tables, but also unstructured data like images or text. And we put this into a machine learning algorithm and out comes a classification result or a regression result. We have different avenues of machine learning. We can compare the sort of traditional machine learning with a more modern deep learning approach. Both are in common that we start from data that could be tabular data or images or text. And then in the lower part we have the traditional approach. So if we don't have structured data already, like images or text, we need to convert those into feature variables. And this is called feature engineering, and this is done by a human expert. So these are people who are very familiar with the domain we work on, and they can, for example, extract key elements of the image and translate this into numerical values. So at the end, we have a table. And if we already start from a table, we can also invent new variables. And this is then fed into a machine learning algorithm, for example, a decision tree or a small neural network, and out comes the prediction. Deep learning works slightly differently. Here the two steps are combined, and we don't have a human expert that defines those features or performs the feature engineering. But the deep learning approach sort of learns all those features itself. So for example, we have a very powerful and complex neural network, and so to speak, the first part of this neural network is to learn the features from the data, from the images and from the text, and sort of the second half of the neural network is then the classifier, for example, to determine what kind of details we see on the image. So feature engineering is done by human experts that design variables, and they need to have a deep understanding of the application domain. When we want to develop features, we want to have variables that have high correlation with the variable we want to predict. This is called the label, and low correlation with all other features. We also need to measure this feature importance so we can identify which features we want to use and which maybe we want to discard. So for example, we could shuffle the values of a variable and retrain our model and observe the decrease in performance. So if there's a very small decrease, then probably this variable doesn't contribute very much. We could also use so-called Shapley values. Here we interpret in a way the features as a team, and each feature is a player in that team, and together they achieve a given performance, and the Shapley values allow us to attribute how important one of these features is to the team. When we have many features, we also want to find a way to build sparse models and reduce the numbers of features, and this we can do with the L1 norm as we add as a regularization approach. And then the machine learning training will sort of favor those models that have few variables. But the underlying assumption of all of this is that the data are representative of what we want to learn. Now let's stop here for a second and think about what this actually means. We assume that the data are correct when we give it to the machine learning algorithm, because we assume that the machine learning algorithm can extract an implicit model from this data. So if the data are not correct, this model will be wrong. And we also have relevant features that describe what we want to learn. The machine learning essentially exploits the correlation between those feature variables and the target or the label or the variable you want to learn. We need to distinguish between two kinds of correlations: the linear correlation, that is typically expressed as the Pearson correlation coefficient, and non-linear and higher order correlations. These are a bit more difficult to understand, but the machine learning algorithm will use them. So what do we mean by this? In the simplest way, we have the Pearson correlation coefficients between two variables. And we can see this in the top two rows of the illustration here. If those two variables are unrelated to each other, then the correlation coefficient will be close to zero. And this is like the block in the middle. And as these variables behave more or less in the same way or in the anti-way, the correlation coefficient will become 1 or -1 as illustrated here. So the covariance is a measure of how do the variables x and y co-vary or vary at the same time. We normalize this by the standard deviation to obtain the Pearson correlation coefficient. However, it only measures linear correlation. We see that in the middle they behave differently, but the Pearson correlation coefficient is always 1. And in the lower part, the Pearson correlation coefficient is always 0. But clearly those two variables are correlated with each other, just not linearly, but there are higher order correlations. And these are also important to understand if we want to use machine learning. So the question is, are the correlations we observe good correlations? Because only those good correlations are something we want to have in our model building. Because machine learning exploits these correlations, so we need to make sure that any correlations that are present in the data really describe what we want the machine learning algorithm to learn. Just remember, correlation does not imply causation. Correlation can also be meaningless or random. It's also called a spurious correlation. So if we have these kind of correlations between variables in our data, the machine learning model will learn the wrong relationships. One example to illustrate this is the sociology PhDs and the number of space launches in the US. And if you look at the behavior of those two variables against time, they are highly correlated. But of course, the number of sociology PhDs and space launches has no causal relationship to each other. So this is an example of a spurious correlation. However, if we were to give those two variables to a machine learning algorithm, this algorithm would pick up on the spurious correlation. So when we have features, it's important to understand what we give the machine learning algorithm to learn from. That means we need to decide which features or variables we need to include, and this is again where your domain expertise comes in. A typical approach that is often seen is that we have many variables and then use some feature selection method to remove unnecessary features automatically. However, this makes the issue worse. The more variables we add, the more likely we add random or spurious correlations. So it's really an anti-pattern to just use as many variables as we can think of and then let an algorithm decide which ones to keep and which not. Another critical issue is data quality. We already said machine learning learns from data, and we already said we assume the data are correct. But what happens if they are not? So there are typical issues we can illustrate here in the case of tabular data. For example, we could have missing values or wrong labels or wrong values in the features or outliers. Or we could have different representations of the same thing, for example, true as a boolean versus true as a string versus 1 as a number. Or what often happens in practice is that variables get reused with different meanings. This is very difficult to catch. Another issue is ground truth, the labels, right? Defining labels should be in principle be simple, right? We know what it is. Take cat or dog as an example. Here it's very obvious what is a cat or a dog. But in other cases it's not so easy. So there are nice memes on the internet like kitten or ice cream, parrot or guacamole, sheepdog or mob. We can probably identify all of them at some point, but it's very tricky and very hard for us to do. And this makes it very difficult for the machine learning algorithm as well, because if we make a mistake in assigning those labels, necessarily the machine learning algorithm will learn a wrong relationship as well. So let's go away from cats and dogs. More seriously, as an example, take damage classes and materials, in this particular one in dual phase steel. We have well known from literature damage classes like margin set cracking, grain boundary decohesion, interface decohesion, and inclusions, and we see a typical example here. And defining the ground truth label is easy for like obvious cases. However, it becomes a bit more tricky if the cases are not like literally textbook examples. And this was done in a little quiz and survey, some other lecture. And you can see the people weren't quite sure. Although they are all domain experts, they wouldn't really know what to attribute this. There was no unanimous assignment of the damage class, and hence, depending on who you would ask, you could guess a different answer. And this is what makes labeling so tricky. So when we build a large training data set, we need to add the ground truth labels to each sample, but this is quite difficult for not so clear-cut cases. But we could also not just ignore them, because that would indeed introduce a bias, because then we would only introduce the easy ones and the machine learning wouldn't really know what to do with the other ones. It's also often found that building a new training data set leads to new insights. So the process of getting good and high quality data is a valuable process in itself and often leads to an improved measurement in itself. One of the things we can do is to split the data in test and train and validation samples. So this helps us evaluate the performance of machine learning algorithms. So imagine that we have two classes and all our data can be represented by blue and red rectangles. Ideally, we would want to use all of this for training, but then we cannot evaluate the performance on an independent data set. So we need to split our data into a test and training data set, and a typical value is to use 80% for training and 20% for testing. However, in several cases the test data may be too small, so it's not representative and we don't capture everything. We also may have very little data to start with, so sacrificing, so to speak, 20% of the data for testing alone is already quite painful. And if we have several outliers and rare events that are really not fake data, but they are real, then they must be in the training and in the test sample, so we can see if the machine learning algorithm first of all learns this and how it behaves on these rare events. One of the approaches we can take in these cases is called cross-validation. There we take different sort of splits. We always use 80-20 splits, for example, but we repeat our training several times and sort of permutate around which of the data we use. However, nothing is as simple as it seems, right? The assumption we make here is that the data can be split randomly, that we have independent events. This is wrong for sequence data, for example, sensor data that we record over time, or time series or videos. There we need to split the data into successive but ordered windows. We cannot just shuffle them about, because that would destroy the correlation in the temporal ordering from early to late events. Some best practices to finish off with. So let's start with the features. We need to use our domain knowledge to create good features. Don't just add everything and anything. Understand the correlations between the features and the labels, and also between the features themselves, and try to find causal features in the sense that we understand how these features are related to our target variable from our domain knowledge. Data quality is really important. Invest time in cleaning your data, even if it seems like a boring step to do, but this is actually where you can get the most gains. Once you have a sufficiently well-working machine learning model, spending a lot of time in improving the algorithm may bring a large benefit, but most of the time you get an even larger benefit by cleaning your data and have a good clean data set with clear ground truth labels. Don't just delete any data with missing values, because they might be missing for a reason. For example, in certain circumstances, your measuring equipment may fail, and so there is information in this missing data. Also, deleting data may introduce a bias. For example, if you remove outliers, and these outliers are really rare events, but you only have so few of them, they are real data and you need to learn from them in your machine learning model, unlike those outliers that are introduced by the data acquisition and data handling systems, right? So here you really need to understand which data has which quality. split your data into a test and training sample and evaluate a model on an independent test sample, because only then you can be sure that the performance is representative and that you don't overtrain. Define and set this test sample aside before working, if possible, and you have sufficient data. Otherwise, you use the cross-correlation and beware of sequence data. There's another thing that you need to consider. Sometimes it's not enough to split the data into test and training data. You need to split it into 3 ways, into a validation sample as well. Because some models and features depend on further parameters. They're also called hyperparameters. For example, the learning speed of neural networks, but also the parameters of decision trees. These are things that you can tune. But also some features will depend on further parameters when you build them. And the validation sample is yet another independent sample to tune those hyperparameters on. But the challenge is that in most cases you rarely have enough data, especially for rare events, to define 3 independent samples. So you need to think about carefully how you use the data in your machine learning network to make sure that you get the most gains from it.